The pH scale and pH calculation is going to be what we're covering in this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll leave links in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. All right, before we can talk about the pH scale and pH calculations here, we just got to talk about what's going on inside of an aqueous solution. So it turns out water autoionizes or autodissociates. So look at a water molecule, it can split apart into a pair of ions here. So a hydrogen ion and a hydroxide ion. Now, sometimes we write this a little bit differently here. So it turns out that free H plus is really unstable and it probably doesn't exist freely in an aqueous solution. It is probably going to combine with another water molecule or water molecules, as we'll see. And so sometimes we write this reaction a little bit different. And we write it like so. And so instead of one water molecule splitting to give you a hydrogen ion, if you have two of them, one acting as a Bronsted acid, one acting as the Bronsted base, and you transfer an H plus from one to the other, you get H3O plus and hydroxide. And so in this case, H3O plus is hydronium, and it looks like you've just simply added an H plus to water. Well, the truth is, one of these free H plus ions, again, that doesn't exist, is probably not just actually associated with one water molecule. It might be associated with, two or three or four water molecules all at the same time. And so even this is a little more accurate, instead of saying we have naked protons is a way to look at that in your solution. It's a little more accurate, but even this is not, completely an accurate representation of what's really going on in the solution. So, but whether we just look at it this way as a hydrogen ion constant, a hydrogen ion or hydronium ion, both mean the same thing, and we're going to treat them as equivalent in this chapter, as we'll find out. So when we talk about like the formula for pH equals the negative log of the hydrogen ion concentration. You could just have as simply as written this as, also as negative log of the hydronium H3O plus concentration. Exactly means the same thing, exactly equivalent. So just keep that in mind. Now, if we take a look at this reaction here, you can see that for every H plus you get an OH minus, and their concentrations would be equal in a solution that is pure water. If all you got is water, then these are going to be equal. So when that's the case, it's going to turn out that's going to correspond to a pH of 7, as we'll get there a little bit. And I'm just bringing that up because I figure you're probably a good chance you're already somewhat familiar with the pH scale. So, but it turns out the equilibrium constant for this reaction is just simply equal to the concentration of H plus times the concentration of OH minus. Notice they're both aqueous, and we leave the liquid out here. And it turns out we call this equilibrium constant a special title. It's Kw, just the equilibrium constant for the autoionization of water. And again, you could also write it as H3O plus times OH minus as well, same diff. And it turns out that at 25 degrees Celsius, this has a value of 1 times 10 to the negative 14. And so when we're doing pH calculations, we're going to assume that we're at 25 degrees Celsius unless we're told otherwise. All right, so if we've got pure water, once again, we said that these are equal. And so these two concentrations are equal, but they also multiply out to give you 1 times 10 to the negative 14. And so what you can do is you can take that 1 times 10 to the negative 14 and set it equal to x squared, since these are equal. Take the square root and you'll find out that x equals 1 times 10 to the negative 7 molar. And so in pure water, both the H plus and OH minus concentrations are equal to 1 times 10 to the negative 7 molar. What happens when you add an acid? Well, when you add an acid, it shifts this equilibrium back to the left, and you just put a bunch of H plus in there, and so it's going to cause it to go back down a little bit. But what's really going to happen is you're going to lose the hydroxide when it shifts back to the left in the equilibrium. And so as a result, when you add an acid, you end up getting more H plus and the OH goes down. And so characteristic of an acidic solution is a solution that has more H plus than OH minus. If you add a base, it does the exact opposite. You're putting more hydroxide into the solution, which is going to shift the equilibrium back, consuming up some of the H plus. And so you're going to end up with more hydroxide than H plus instead. And so that's kind of the hallmark. Do you have more H plus in your solution? You're in an acidic solution. Do you have more OH minus in your solution? Well, then you have a basic solution. And it turns out there's such wide range of concentrations that are possible here that it's much easier to use a logarithmic scale. And so this logarithmic scale is the pH scale. So pH is negative log of the H plus concentration. We also have something called the pOH, which is the negative log of the OH concentration. And so if you know the H plus concentration, you can plug it in right there, take the negative log, and you get the pH. So like if you've got pure water, well, in pure water, both the H plus and OH minus concentrations are both equal to 1 times 10 to the negative 7 molar. And so you're just going to take the negative of the log of 1 times 10 to the negative 7 molar, and you'd let your calculator do the math for you, and you find out that that equals to exactly 7. And so pure water, it turns out, at 25 degrees Celsius has a pH of 7. It also has a pOH of 7. If the OH is also 1 times 10 to the negative 7 molar, take the negative log of that, you're also going to get 7. And so the pH and the pOH are both 7, it turns out. And it turns out your pH and your pOH are always going to add up to 14 at 25 degrees Celsius as well. And that actually comes from that KW expression we see right here. If you take the negative log of both sides of this equation and rearrange it a little bit, you get this expression right here that you might remember from high school. pH plus pOH adds up to 14. All right. So the other side, what if you're given the pH or the pOH and you want to turn that into the H plus or OH minus concentration? So again, let's take a look at that pH definition. pH equals negative log of the H plus concentration. You should know that a pH, so P here just means negative log. If I say pH, negative log of the H concentration. pOH, negative log of the OH concentration. P your mom, negative log of your mom. P just means negative log. We'll use it in one other context actually, not P your mom, but pKa, which will be the negative log of the Ka value, which will be another equilibrium constant we get to in a little bit here. So P means negative log, pH, negative log of H plus. Now what if you want to rearrange this to solve for that H plus concentration? Well, you'd either multiply or divide both sides by the negative 1 there, so we'd get negative pH equals log of H plus. And then to get rid of that log, you have to take the antilog, and the antilog is simply 10 to the power of. And so you'll do 10 to the power of both sides. And on this side, it cancels 10 to the log. They're inverse functions and they cancel. And so you'd be left with H plus equaling 10 to the negative pH. And so that's our other equation here. H plus equals 10 to the negative pH. In similar fashion, if you solve this equation for the hydroxide concentration, you'll get that the hydroxide concentration equals 10 to the negative pOH. Cool, and then again, we've got the KW expression, and then the negative log of that to get pH plus pOH always add up to 14. And these are the equations we're going to be working with, and this is important. There's actually 4 quantities going on here. We've got the H plus concentration, the pH, the OH minus concentration, and the pOH. And it turns out they're all mathematically interdependent on each other. If I give you any one of these 4, you should be able to solve for the other 3 using these equations right here. And that's exactly what we're going to do. So we're going to set up a table, and in fact, if you got the study guide in front of you, we're going to fill in the missing blanks on that table. Let's have some fun. All right, so before we dive into the calculations themselves, we just want to investigate this pH scale just a little bit more. And so again, if you've got pure water, you've got a neutral solution, we say, and your pH is exactly 7. So, but if you add an acid, you're going to end up with more H plus than OH minus, and that's going to cause your pH to go down. And so any pH that's lower than 7 is going to be acidic. Now, it turns out your pH is not bounded on a logarithmic scale. It's actually not bounded by 0. If you have a really concentrated strong acid, you can actually have pHs that go negative a little bit. So just keep that in mind. Other end of the scale, your bases, if you got a base in your solution, you're going to end up with more hydroxide than H plus, and your pH is going to end up being higher than 7. Also, it's not bounded by 14. A lot of people think, oh, 14 is the limit. It turns out it's not. Again, on the logarithmic scale, there's technically no limits here. And if you have a really concentrated solution of a strong base, you can get pHs that are higher than 14. Now, most of you guys are going to be familiar with the pH scale like this, and you can tell if a solution is acidic or basic based on if the pH is lower or higher than 7. But being able to figure out if a solution is acidic or basic based on the pOH or based on the H plus concentration or based on the OH minus concentration can seem a little bit tricky and confusing. So if you're asked to figure out if a solution is acidic or basic, I highly recommend whatever you've got, you turn it into a pH and go from there. One other thing you should know about this pH scale is that it is a logarithmic scale. every unit you go up or down in pH is a power of 10. So like if you compare, say, pH 7 to pH 6, which one's more acidic? Well, pH 6 is. The question is, how many times more H plus does it have? Well, one pH unit is 10 times more H plus. So at a pH 6 compared to pH 7, you have 10 times more H plus. Well, what if I compared pH 5 to pH 6? Well, pH 5 would have 10 times more H plus than a solution that's pH 6. So if pH 6 has 10 times more than pH 7, and pH 5 has 10 times more H plus than pH 6, then pH 5, how many times more H plus does pH 5 have than pH 7? Well, 10 times more than 6, and 6 is 10 times more than 7, so 10 times 10 would be 100 times more. And so a pH 5 does indeed have 100 times more H plus than a pH 7. And you can kind of look at it as being kind of 10 to the change or difference, not really change, but difference in pH. So between 5 and 7, there's a difference of 2 pH units, and 10 to the 2 is 100 times more H plus at pH 5 than at pH 7. Cool. Works the same way the other way if you want to look at hydroxide instead. So if I said, who's got more hydroxide, pH 7 or pH 8? Well, pH 8 has more hydroxide. How many times more? 10 times more, because it's one pH unit away. What if I said pH 9 compared to pH 7, 100 times more hydroxide. pH 10 compared to pH 7, 1,000 times, 10 to the third times more hydroxide. And so you can do it on the basic side with hydroxide, or on the acidic side with H plus. But it turns out you could look at the entire scale in terms of H plus, or the entire scale in terms of OH minus if you wanted to. So if I wanted you to compare, a pH of, say, 1 with a pH of, at the other side of the spectrum, say, of 10, and I want to say which one has a greater concentration of H plus. Well, the more acidic solution does. Which one has a greater concentration of OH minus? Well, the more basic solution does. But if my question was, how many times more H plus do I have at pH 1 than pH 10? 10 to the 9th, which is a billion times more. So 9 pH units lower, 10 times more H plus. What if I said, how many times more OH minus does the pH 10 solution have than the pH 1 solution? And again, it's going to be 10 to the 9th times more OH minus when you're at pH 10 than at pH 1. Cool. So just want to make sure you realize this logarithmic scale. So we use these in a variety of places, in everyday life, and we don't even realize it. We don't realize how big of a difference it is. You might just be like, oh, pH 7, pH 8, who cares? What's the difference? No. pH 8 is got 10 times more hydroxide than pH 7, things of this sort. So you might see, also see this, say, for earthquakes. The Richter scale, it turns out, is at a logarithmic scale. Now, it's not log base 10, so it's not like, as you go from an earthquake of 5.0 to an earthquake of 6.0, it's not 10 times worse or 10 times stronger earthquake. It turns out it's 31 times stronger. So you might just be like, oh, 5.0, 6.0 on the Richter scale, big deal, no difference. No. It's 31 times more powerful earthquake. What if I go from like a 5.0 to a 7.0? Well, now it'd be 31 times 31, over 900 times more powerful earthquake at 7.0 on the Richter scale compared to 5.0 on the Richter scale. So makes a huge difference when you realize that, oh, that's a logarithmic scale. 1 degree to the next is a huge difference. Same thing on this pH scale. Every pH unit away is 10 times more of either H plus or OH minus, depending on which way you're going. All right, so now we're going to take a look at some calculations here. In every space on this lovely table here, I've given you one of the 4, and we're just going to calculate the other 3. And on your study guide is also this lovely diagram here, which shows you how you can convert one of these to any of the others. So in this case, the first one, we're given the H plus concentration. And from the H plus concentration, I could just directly calculate the OH minus concentration using the KW expression, or I could just calculate the pH directly using the definition of pH being negative log of the H plus concentration. But if I wanted to calculate the POH, I don't have a direct calculation. I'm going to have to do it in 2 steps in one of 2 different ways. All right. So also, if you're dealing with nice round powers of 10, where you've got like 1 times 10 to the something, so life is good. A lot of those you'll learn to do in your head a little bit, so I still highly recommend pulling out your calculator. especially if you're not good with logs and stuff like this. So, however, it turns out when you've got a 1 times 10 to the something, well, anything times 1 is itself. And so 1 times 10 to the negative 7 is no different than just simply saying 10 to the negative 7. Now, if you've got 3.2 times 10 to the negative 8, that's not the same as just saying plain old 10 to the negative 8, because multiplying by 3.2 doesn't leave, doesn't leave something unchanged. So, but if you've got just 1 times 10 to the negative 7, just treat that as 10 to the negative 7. And what's nice is 10 to the power of, that's the antilog. And when you take the log of the antilog, they cancel. And so taking the log of 10 to the negative 7 just gives you negative 7. But taking the negative log of it changes the sign and gets you positive 7. And so if I take the negative log of this, I'm going to get a pH of 7. And so we can do that pretty quickly. And so here in this case, if I've got from the H plus to the pH, well, for me, I like going this direction and going to the pOH. I find it much easier to add two things up to 14 and figure out which one I don't know than multiplying to give 1 times 10 to the negative 14 instead. And so from here, I'm going to jump straight. pH is 7. Well, 7 plus what equals 14? Well, plus another 7. And then the OH concentration is just 10 to the negative of whatever your pOH is. And so this is going to be 10 to the negative 7 molar, which is the same as 1 times 10 to the negative 7. Whether you want to put the 1 or not, it's the same thing either way. Cool. And we only started with the H plus, and we filled in the other 3. Let's do another example. So here we've got a pH of 3, and my first question for you, is that an acidic solution or a basic solution? And hopefully you said, oh, that's a pH lower than 7. That's an acidic solution. And so where do you want to go from here? From the pH, we could either get the H plus or the pOH pretty quickly. So let's get that pOH then. And in this case, what do I have to add to 3 to get 14? Well, we're going to add 11 to that. So the pOH is 11. And then to get the H plus and the OH minus, well, H plus just equals 10 to the negative of whatever your pH is. So this is going to be 10 to the negative 3 molar, which is the same as just 1 times 10 to the negative 3 molar, same diff. And over here for the OH, it's just 10 to the negative of whatever the pOH is. And so 10 to the negative 11 in this case molar, which again is the same as 1 times 10 to the negative 11 molar. And we just filled in that whole column. Let's move on. So now I've given you the hydroxide. Oh, actually, no, I'll leave that alone. So now I've given you the hydroxide. And so where do you want to go from here? Well, with the hydroxide concentration, we can get the pOH pretty quickly. So, and you can get the H plus, but again, I hate this route right here. I hate having to multiply to give 10 to the negative 14. So because I struggle to do that in my head much of the time, but you can go that route. But for me, if I've given the hydroxide, I'm just going to turn that into a pOH. And once I turn that into a pOH, I'll then turn that into a pH, since pH and pOH add up to 14. And then once I've got the pH, I can go back to the H plus. I just hate this part of the path. If you like it, great. All right, so with the hydroxide being 1 times 10 to the negative 10, then I could take the negative log of that to get the pOH. And the log of 10 to the negative 11 is negative 11. The negative log of 10 to the negative 11, oh, where am I at? Sorry, let's try that again. The log of 10 to the negative 10 is just negative 10, but the negative of the log of 10 to the negative 10 is going to be positive 10. Cool, and if the pOH is 10, well, then the pH it's going to have to be 4 so that they add up to 14. And then if the pH is 4, well, the H plus is going to be 10 to the negative 4 molar, which again is the same as 1 times 10 to the negative 4 molar. Now my question for you is this solution acidic or basic? Well, if I often ask students that before we've actually calculated the pH, and a lot of students will look at this and very quickly they'll be like, oh, 10, that's basic. Oh, that's pOH, and it's backwards from the normal pH scale. And that's why I said just turn it into a pH. Look at that pH to figure out if it's going to be acidic or basic. And in this case, any one of these numbers can ultimately tell you this. If your pH is less than 7, though, that's the one we're most used to seeing, that's going to be an acidic solution. If your pOH is greater than 7, that's an acidic solution. If your H plus concentration is greater than 1 times 10 to the negative 7, that's an acidic solution. And if your OH concentration is less than 1 times 10 to the negative 7, that is an acidic solution. So lots of things can tell me this is an acidic solution, but the one that is most reliable to get right is just looking at that pH and seeing if it's less than 7. All right, next one, we've got a pOH of 2. So in this case, with a pOH of 2, a couple places we can go. With the pOH, we can get the pH pretty easily. We can get the hydroxide fairly easily as well. So I'm going to get that pH first, and the pH here is going to be 12, since that's what I have to add to 2 to get 14. And then the OH is just going to be 10 to the negative 2 molar. And the H plus concentration would be just 10 to the negative 12 molar, which is the same again as 1 times 10 to the negative 12 molar. Life is good. This is not so bad. When you've got nice whole numbers for pHs and pOHs, you're going to probably get to a point where you can do this pretty reliably in your head. I think using your calculator to check your answers is always a good thing. But what if it's not 1 times 10 to the something? Well, then that's time to pull out your calculator here. Now, it turns out if it's 3.2, you can probably do it in your head as well, because that's exactly the halfway point. It turns out that 3.2 is the square root of 10, so which becomes relevant if we kind of split this up into some powers here. But in this case, I'm just going to recommend you use your calculator. Now, one thing you should know here, when you take the negative log of a number, so as that h plus goes up, that pOH is going to go down. So let's just say for a minute that this was a 1 times 10 to the negative 8. Then the pH would be 8. But since this number is now bigger than that, bigger than 1 times 10 to the negative 8, then your pH is going to end up smaller than 8. It's going to be 7 point something. So at the very least, I can approximate. I know it's going to be 7 point something. So if I had a multiple choice test and there's only one answer to the choice that said 7 point something, I'd pick it. So, however, let your calculator do the work for you. And so in this case, if we take the negative log of 3.2 times 10 to the negative 8, we're going to get 7.5. So, and if you go to take the MCAT or the DAT or the OAT someday, they're not going to give you a calculator on your chemistry section, and I will teach you how to do these calculations or at least approximate them in your head. But for now, in your Gen Chem class, by all means, do this with a calculator. All right. Now, if the pH, so we started off with the H plus, we got the pH, and I'm going to move on to the pOH. And again, what do I add to 14? Or I'm sorry, what am I going to add to 7.5 to get 14? And I highly recommend you probably do this with your calculator. When it's nice whole numbers, life's not so bad. When they're not whole numbers, for some reason, adding to 14 is such a pain in the butt. And so here, if we do 14 minus 7.5, you're going to get 6.5. And like I said, something about it that just makes that math challenging for subtracting from 14 there. Now we can go to our hydroxide, and hydroxide is just 10 to the negative pOH, and so we're going to put in 10 to the negative 6.5 molar, and we got a problem. Now, if I'm just doing some work along the way, no, I don't care. But if I'm looking for the answer on the, a multiple choice test, and I'm looking for that answer to be my hydroxide concentration, it's not going to be there. And so you've got to take your calculator here and put in 10 raised to the power of negative 6.5 and let your calculator tell you what this is equal to. And it's going to be 3.2 times 10 to the negative 7 molar. So this is not proper scientific notation here. 3.2 times 10 to the negative 7 molar. And again, that's what I plugged into the calculator, though, that improper 10 to the negative 6.5. That's exactly what I put in my calculator. I just let my calculator express it in proper scientific notation. Cool, and now we've filled in this entire box. So big takeaways here. So you should understand some things about your pH scale, logarithmic scale, and things of this sort. You should know how to do all these lovely calculations at 25 degrees Celsius. And again, we're always going to assume 25 degrees Celsius unless we're told otherwise. And in this case, given any one of these four, you should be able to calculate the other three. Now, one last thing on this. What if you get a question where you're not at 25 degrees Celsius? What if they told you that, say, Kw was 1.0 times 10 to the negative 13, and let's just say this was at like 37 degrees Celsius. So like body temperature, right? So, and they said, oh, it's not 1 times 10 to the negative 14 anymore, it's 1 times 10 to the negative 13. And what are the implications of this? Well, keep in mind that your Kw, again, is still equal to the H plus times the OH minus, which is now going to equal 1.0 times 10 to the negative 13 at this new temperature. So again, if they don't tell me anything about temperature or anything, I'm just going to assume that these multiply out to give me 1 times 10 to the minus 14 and that we're at 25 degrees Celsius. But if in the question they give us something like this, well, it means they're on their way to asking you something specific. So it turns out that when this multiplied out to give 1 times 10 to the negative 14, so That's where the idea that pH and pOH adding up to 14 comes from. Well, now it's not going to add up to 14. It turns out, in this case, I picked a nice round number, it's going to add up to 13. It's also from where we get the idea that, neutral pH is pH 7. Well, not at this temperature anymore. And so what we do is, again, in pure water, these are still going to be equal. And so x times x essentially is going to equal 1.0 times 10 to the negative 13. And x is going to equal the square root of that. So we'll take the square root of 1 times 10 to the negative 13 and get 3.2 times 10 to the negative 7. And if we take the negative log of that, then we can find the pH as well as the pOH. Since this is equal to either one of these, it's equal to the H plus and it's equal to the OH minus concentrations. And so in this case, we'd find out that it's actually equal to 6.5. Both the pH and the pOH. And notice 6.5 plus 6.5 adds up to 13. And so at this new temperature, the pH and pOH don't add up to 14, they add up to 13. And neutral pH is no longer 7, it would be 6.5. These are equal again in pure water, but they're not equal to 1 times 10 to the negative 7 molar. And the pH and pOH are not equal to 7 anymore. In pure water, they're now equal to pH and pOH of 6.5 instead. A pH of 7 would actually be basic at this new temperature. Now I'm just making numbers up here. I have no idea what the KW value is at 37 degrees Celsius off the top of my head or anything. I just want to see a context for which you might be asked a little bit more. And this is the one context where you're likely to see them give you the KW at some other temperature and then ask you, is pH 7 still neutral? Or is it acidic or basic? Or they might say, what is the new neutral pH? 6.5, things of this sort. But the key is you're just setting x squared equal to KW to find out the new concentrations of OH minus and H plus that are equal to each other in pure water at this new temperature. Now, if you found this lesson helpful, hit that thumbs up button. Best thing you can do to support the channel. It lets YouTube know to share this lesson with other students as well. And if you're looking for practice problems for pH calculations or for anything else in general chemistry as well, my general chemistry master course includes over 1,200 practice questions, final exam rapid reviews, practice final exams. I'll leave a link in the description. A free trial is available. Happy studying.